So, in this class now we will continue with the acquisition parameters, that is the different parameters which is required for setting up an NMR experiment. We saw in the last class a few important ones such as the relaxation delay between the scans, the 90-degree pulse width, locking, shimming, etc., and that is before the pulse is applied. Now, what we will see now is what are the parameters to be looked at after the pulse, that 1D pulse is applied. So, this is shown here. This is the 90-degree pulse which is shown as a typical pulse program. So, we saw before this what all we have to do up to this point. Now, after the pulse is applied, then you have the signal which is called FID. So, this is the induction current EMF which is induced in the coil, and that is detected as an FID. So, now if you recollect, this depends on the T2. If the T2 is short, the signal goes down very fast. If the T2 is long, the signal will stay longer. That means this is oscillation. The oscillation depends how long the oscillation will happen forever, but it is reduced in amplitude because of this T2 relaxation, and the T2 relaxation reduces the intensity, and at some point it goes to 0. So, the acquisition time, how long do you record an NMR signal depends on what is this T2 of the sample. So, in the previous class we saw that we should have a rough idea of the T1 because we need to set up the relaxation delay. In this particular case we need to know the T2 of the sample. So, we need to know both T1 and T2 of a sample for recording any NMR experiment. Again remember, T2 is something which you may know, and T1 and T2 will not know exactly for your sample. It may be a new compound every time you record. So, you should get a rough idea. So, again based on the size of the molecule typically the T2 values can be predicted. So, how long then this should be the time taken? This is typically the time taken about 3 times the T2, because after 3 times the T2 the signal has gone completely to 0. So, this is this can be mathematically shown like this, which I will show you, which I will derive now here. So, the intensity of this FID is equal to I0 into cosine the frequency, that is oscillation in time dependent, into e to the power minus t by T2. So, this is the FID, this is the form of the FID, this is what we saw in the last class. Now, if you look at this parameter here, this is causing the decrease in the intensity with respect to time. So, if I take t equal to 1 times T2, then your I is basically I0. Let us ignore this term, say cosine some frequency, that does not depend, because that is just an oscillation, but here you see it becomes minus 1 because t is equal to T2. Now, this is 1 over E. So, 1 over E is 1 over 2.7. This is 1 over 2.7 E. So, this is about 30, so it has reduced to about 33%. So, you see it was earlier, this is if you consider I0 as 100%, now I0 by 2.7 is roughly 33%. So, the signal has decayed by 33% in 1 times T2. Now, if I take t equal to 2 times T2, then it will be here, if you look at here, it will be I equal to proportional to e raised to minus 2 e square, which is now further gone down by square of this. So, which is about 90%. So, in about 3 times T2 the I will be almost equal to 90 only 1% or 5%. That means, the signal has come down from 100% in the when it is here when t is equal to 0 to 5%. So, this reduction has happened because of using 3 times T2. So, by 3 times T2 the signal has reduced by 95%, and that is what we have to keep in mind, that when you set up this time delayed acquisition time, it has to be 3 times T2 and not more. If you give more than 3 times T2, if you look at this here, it will further go down to 1% or lesser than that, but then the signal is not present, but the noise will start coming, because noise is present always, remember. So, noise is which is present coming from the electronics of the system, the hardware, and that comes it picks up from various sources down this line, and all the noises also are accumulated or are collected in FID. So, FID is a combination of signal and noise. So, if signal is gone to 0, but the noise never goes to 0, it is constantly always present. So, at some point your signal is 0, but the noise is present. So, signal to noise is 0 because signal is 0. So, this is what is the problem, that if you record this experiment for too long a time, then you accumulate noise, but there is no signal and the signal to noise goes down, and therefore, this is one of the practical reasons why many times people come up with the argument saying that they are not getting any signal in their sample, and the reason being they used a very wrong acquisition time, and they would have used probably 10 times T2 without realizing, because T2 is something you should have a rough idea, and if you wrongly estimate T2, then you will end up with if you overestimate T2, you will end up with using a very long time, and what happens is the signal has gone to 0, but the noise has accumulated. So, signal to noise goes down if you use a very long acquisition time. So, acquisition time has to be optimized based on the T2 value, again based on the experience. If you look at typically the organic molecules which we study in the laboratory, or if you consider biomolecules, we look in this range 100 milliseconds to 300 milliseconds. So, in NMR spectroscopy one has to keep in mind these different time values. This is very important because as we go on, it is one should have a feel of what are the different time scales you are using. For example, when we say pulse width, you should know that it is in the order of microsecond. If you look at relaxation delay, you should know it is in the order of seconds, and if you talk about acquisition time, one should know that it is an order of 100 milliseconds. So, these are the different time scales, and one if one makes a mistake in this time scales remembering, then the acquisition and the spectrum becomes pretty comes out bad. Now, the next step is again after you when you are recording the signal, there is a hardware component called as a receiver. Again, as the word receiver suggests, it is basically receiving the signal. So, if you want to receive the signal, you want to receive at the maximum amplitude. So, therefore, you want to increase the intensity, the amplitude of the FID, it is amplified by then adjusting the gain in the receiver. So, this is what is done, this amplification is done so that maximum signal reaches the ADC. What is an ADC? ADC is called analog to digital converter. So, ADC is what is the next step after we record the signal, we will see that, and that signal to maximum signal to reach ADC, one has to therefore increase the receiver gain, and receiver gain is simply what is doing is it is simply amplifying, it is just scaling up the signal, but remember noise is always there in the signal. So, the noise also gets amplified. So, receiver gain is basically what it is doing, it is amplifying signal as well as noise. So, both signal and noise are amplified, and then that is fed to the ADC. So, this is where the dynamic range issue comes into picture. What happens is this ADC has a limited capacity to receive signal, it cannot arbitrarily receive any large amount of signal that you give. So, let us say you have a solvent signal in your sample, and the solvent, if as I mentioned in the last class, the solvent suppression is very important. You have a huge signal to noise dynamic range, and therefore, if the signal solvent signal exceeds the range of the ADC, then we end up with what is called ADC overflow. You can think of ADC overflow in a similar manner, like let us say you have a water tank. A water tank fill some amount of water. If you fill more than that, it will start overflowing. So, similarly ADC has a limited capacity to hold the signal strength, and if you have more signal strength than what it can take, it will start overflowing. So, what is overflowing? It will simply subtract, or it will simply omit the signal. Okay. So, this is the second important step. Then what we come to the more important practical point is the scans. So, this is what we also use the word transients in NMR. The number of scans is basically how many times you want to average. So, if you remember in one of the classes we mentioned that in 1D NMR you record the signal many number of times, you do not record it only once, you record it many number of times, and this many number of times each time the signal is added, and then what you get is a final addition. Of course, the noise also gets added, but remember we said that noise does not increase as much as the signal increases when you add, because noise is a random white noise. So, it starts subtracting itself. So, it goes slowly. So, if you do it for suppose you do as 2 scans, when you do a 2 scans, the signal will go by twice, but the noise will not go by twice, it will go by square root of 2. So, because of that the signal to noise overall increases by square root of the number of scans. So, if you use 16 scans, your signal to noise compared to 1 scan, if you use 16 scans, then signal to noise will go up by a factor of square root of 16, which is 4. So, depending on the signal to noise, one has to basically give a large number of scans. So, again coming to from a practical standpoint, in organic chemistry and in the standard biomolecular peptides which we use which we record, typically about 8 to 16 scans are given. But again remember, this is for a 1 millimolar sample, a sample concentration where it is around 1 millimolar or more. We can record good data with 8 or 16 scans. But if you go to carbon 13, remember carbon 13 we will see later that it is very insensitive compared to hydrogen. Why? Because the gyromagnetic ratio is less 4 times and the natural abundance of carbon 13 is also less. So, because of that you need more scans, and as written here, if you have a good concentration, typically let us say you have a 5 millimolar sample or 10 millimolar sample, then you need to record you can record a good data set with at about 256 scans. Okay. So, carbon 13 remember is very less sensitive. So, this is the solvent suppression part which we had a brief look at it in the last class. We will not go in detail, but I would just like to tell you about what a very most basic type of solvent saturation which is used very routinely, that is called as PreSaturation. So, PreSaturation is shown, the picture is shown here. So, this is called a pulse sequence again. So, remember before we apply the 90-degree pulse, this is the 90-degree pulse, we apply what is called as a PreSat. This is a nothing but a low power continuous RF radio frequency, not a pulse now, because pulse means it is in the microsecond. But look at this delay, this is about, remember this is called relaxation delay, and this is of the order of few seconds. So, for the entire relaxation delay period, what is done is a weak RF is applied on the solvent at the frequency of the solvent. So, when you apply a weak RF on the solvent frequency, what happens is you irradiate the solvent, this is called irradiation, and you equalize the population, of the alpha and beta state of the solvent. So, if you have to you recollect that we talked about 2 energy levels in NMR, alpha and beta for spin half nuclei. So, water for example has proton, and proton has alpha and beta states, but selectively if I apply a continuous RF only on the water protons, then the water proton populations between alpha and beta gets equalized after a long time, after a certain time, and that is called saturation. We will not be able to go in details of how that particular saturation happens, but the idea is very simple, that you take the solvent, the signal, the chemical shift value of the water protons, and you apply at that frequency a weak continuous RF. Weak means is a really weak signal. This is the strength of this signal is typically about 50 to 100 hertz. Remember in NMR when we talk about strength of a irradiation, we talk in terms of hertz. So, this is typically kilohertz, the 90-degree pulse width, but this is typically 100 hertz, 50 to 100 hertz. So, at that frequency the 100 hertz is the range of the amplitude of the irradiation, but it is applied on the water resonance or the water proton, the solvent proton. So, because of that the solvent proton populations get equalized, and remember when the populations are equal, the population difference is 0. So, when population difference is 0, no NMR can be done. So, that means what this process is doing, it is trying to make the solvent signal become 0 by equalizing the population. So, you can, it is like a weak irradiation, we also use the word saturation, and hence the word PreSaturation comes, PreSaturation because it is applied before this 90-degree. Then you apply 90-degree pulse in for a general for all atoms, for all nuclei, all spins in that molecule. So, what will happen when you record this signal here, there will be no contribution to the FID from the solvent, because solvent has been already killed or eliminated from the spectrum by irradiating. So, the oscillations, that is the chemical shifts what you see will only come from the compound peaks, and the solvent peak signals are or oscillation is gone. So, when you do a Fourier transform and finally get a spectrum, your spectrum will not contain any solvent peak. So, this is one way to do the solvent separation, but this is a very crude approach, a brute force approach. We use the word brute force. The reason being, you are simply doing a just applying a hard radiation or irradiation at a weak radiation at the solvent line. So, this is not really the best solution many times, and therefore, pre-saturation, although is used, is the most common approach, is not the best approach. The best approaches are more advanced, called water gate, wet, etc. We will see that not now, but in the third or fourth half part of the course, where we look at more advanced topics. So, once the data of NMR data is recorded, this next step is to do what is called processing the data. So, remember what data comes out in NMR is called FID, and FID is basically the raw data which is recorded physically by a signal, by the spectrometer, but that is not what is the spectrum. The spectrum still has to be obtained by massaging the raw data, and the raw data is massaged by doing many things, then it is converted into a spectrum by Fourier transform. This is a mathematical technique, which is why the word FT-NMR is used, but even after Fourier transform, the data is not completely ready to analyze, because there are certain things which we have to further do on this NMR spectrum, and that finally after all these steps is what we say that the spectrum is ready for analysis. So, we will see these steps now one by one. So, the first thing is called applying a window function, or this is a Greek word apodization. So, what is this thing? What do we do in window function is the following, that if you remember the FID, let us go a little further to see this FID, and we will come back to the previous slide. So, this is an FID, this is an FID, oh sorry, this is an FID. So, you see this is called a raw FID. Raw means it is the crude FID which is coming out of the sample, and this is what is captured by the preamp, and then this is stored in the computer in a digital form. This is what is digitized. Now, we have to convert this into a spectrum. So, before doing that, we do what is called apodization. Apodization is like multiplying this whole signal with a exponential decay. So, if I multiply this line, what you are seeing line here, if I multiply with this FID here, I will get this is the answer, this is the output. So, you see the signal is going down, down, down slowly and finally going to 0. Why this happened? Because this is coming of this exponential decay. Because of the decay, the signal has gone to 0. So, you see what we have done is we have forced the signal to go to 0. The signal was not going to 0, there was of course signal is already 0 somewhere here, and all these things what you are seeing is noise. So, this is how the noises look like. So, the signal is present only, you can see clearly the signal here, that is FID more clearly only this side. This part of the FID is only noise or signal, a little amount of signal with noise. So, therefore, we do not want to have this portion, because this portion if I can include in my processing, my signal to noise will go down. Why? Because the noise is only present and signal is absent. So, therefore, we try to filter means we try to stop the data here, and what we do is we only now take this part of the data, and this part is anyway 0. So, this does not contribute to signal. So, you can see this is what happens. So, this is your signal. If I do not apply any window function, means if I take directly this, you should look at this picture here. If I directly take a Fourier transform of this FID, I will get a spectrum like this, peak like this, and signal to noise has been shown to be 27.8. This is from the book by, this whole thing has been taken from this book by Keeler and Pavia. So, one of the books, all this book explains. So, the picture is taken from there, and then you can see the signal to noise has been calculated to be 27.8. That is the height of the signal divided by the height of the noise. But now, when I do an apodization, I smoothen the signal, I mean I apply truncation, this is called a window function, and you basically make the signal go to 0, and when I do a Fourier transform, I will get a peak like this. So, if you compare these two pictures here, you see this picture looks much better, the second one, because the noise level has gone down. But what has also happened is your signal height is also gone down. Okay. So, why the signal height has gone down? The signal height has gone down because the peak has become wide, peak has become broad. So, it was earlier 1 hertz was the line width, here it has become 2 hertz. So, obviously the height will go down. Remember, in NMR the area is always constant, because the area under the peak, it gives you the number of hydrogens. So, for the same sample, whatever I do, my area under the peak should not change, because that is the important point, because that is what I need for my quantification. So, the area of the peak does not change, then if I increase the line width, I have to compensate by reducing the height. So, automatically the height is reduced, so that the area is kept constant, but here the noise has gone down also very high, now down a lot. Therefore, when I take a signal to noise value, I will get better value compared to this, is almost double. So, you see, by doing this exercise of a window function, I can improve my signal to noise tremendously. Of course, this is not always a factor of 2, it can vary from any way, but typically it can go from 1.5 to a factor of 2, 2.5. So, that is why it is very important to do window function. Again, in nowadays spectrometers, these are done automatically by typing some commands. So, most of the users or students are not aware of what is happening behind the screen. So, therefore, this slide is basically meant to show you that what happens when you process the data. So, there are different ways to apodize the signal. You can take only the first part of the signal, you can multiply with different functions, these are called window functions, and based on that you have to we can do the processing. So, one thing important to note here is the resolution, and this is a very important point in NMR. So, one thing a theory of NMR which we will not go into detail, but it comes from the Fourier transform, that the signal is basically present in the beginning. If you look at the FID here, what is happening is the signal is present in the beginning. As the signal time proceeds, the signal goes down to 0. So, that means your sensitivity is all focused in this side. So, if you want to get a very good signal to noise like we saw in the last slide, then your emphasis, that means your focus should be on this part. That means you should not give too much importance to this side. When you say too much importance, it means you multiply with a function which takes this part to 0, and what is more important is this part. But let us say you are not interested in signal to noise improving, you have very good signal to noise anyway, and your interest lies in the resolution, means you want to separate a peak. If you want to do separation of peaks better, then this portion of the spectrum plays a role, the later part of the FID. Now, how do you rationalize this, how do you understand this? This can be understood by a simple analogy. Let us say we have two trains moving at, let us say one moving at 100 kilometers per hour, another moving at 102 kilometers per hour. That means there is only a difference of 2 kilometers per hour between the two trains. Now, I start the race, the two trains start at the same time, but initially they are moving at the same speed, I mean same distance, the distance separation between them is not going to be visibly different. Only when you wait for a long time, then the trains would have really separated in real time and separated in time space by a large distance. So, therefore, if you have two signals, means two frequencies which are very close, that is like the speed of the train, then you need to wait a long time in the FID for them to be really separated from each other. In the beginning, the two frequencies will look very much alike. You will not be able to say that there are two frequencies here, but only if you wait for a long time towards this side, then you will start seeing that there are two frequencies. What it means, that your resolution, that is the separation between the peaks, appears on this side more than what appears on this side. So, that means if I want to get a better resolution, my emphasis or weightage or importance should be given to this part of the spectrum rather than going to this part, and that is again done by using different mathematical functions, that is the window functions, and you can look at this kind of a function here. What is happening here, if you see, it is giving very less weightage to this part. So, this is multiplied with the FID, this is the raw FID. If I multiply with this is what shown here into FID, I will see that the initial portion is going to 0, but I am giving more importance to this part. So, therefore, my separation will become better and better, but the signal to noise will go down. And why is that? Because the spectrum is given less importance here, which is where the sensitivity is there. So, the signal to noise goes down, but the resolution improves. So, therefore, in NMR, that is the major standard thing which we say, that if you want to gain sensitivity, you have to lose resolution. Why? Because if I want this part of the spectrum, this portion I have to sacrifice, that is where the resolution is there. But if I want to get resolution, then the sensitivity I have to sacrifice, because resolution is on the other side, second half, the sensitivity is not so much there. So, the resolution and sensitivity are kind of complementary, and to gain one you have to lose or trade off the other. So, this is what is shown in this slide also, that if you want look at this here, the emphasis is given on this part of the signal, and therefore, the line looks broad. But if I want to get a better resolution enhancement, then I will give less weightage to here and I will give more weightage this side. So, you can see here that lines are now, you can see some resolution, means the lines are getting sharper and there is a separation. Here you cannot make out how many lines are there, peaks are there, but here you can start seeing the peaks. But of course, not shown here, but the sensitivity goes down because of less weightage given to the beginning. So, the next step is to then Fourier transform the spectrum and by applying the apodization, and you get a peak. This slides basically talks about what is called truncated FID. What it means is that suppose you have an FID which you do not complete. Remember, we mentioned in the last class that the acquisition has to be or in this class in the beginning we saw the acquisition time has to be 3 times the T2, but that does not always happen. There is a decrease in the signal to noise if you do not record, and when you truncate the FID, this is called truncation, you will get bad spectrum because of what is called as wiggles, and to improve that we apply this window function and do Fourier transform. So, we will come to this end of the class today. In the next part we will look at how the signal spectra, now once we have recorded the spectrum in different and process the data, we will now start looking at how it can be analyzed and the data can be interpreted.